So in section 8.2, we're going to be talking about the geometric distribution. The geometric distribution is similar to the binomial distribution in a lot of ways, but there is one important distinction between the two, and that is what it is that you're actually trying to calculate. In the binomial setting, you were looking at the probability of success for a certain number of outcomes. So see, if we go back to our free throw example, we were looking at the probability that the basketball player would make 6 free throws out of her 12 attempts. In the geometric setting, we're looking for something slightly different. In this case, we're actually looking for when we expect the first success to occur. So it's a slightly different question that we're asking if we're using the geometric distribution, but a lot of this is going to look very similar to the binomial distribution. So first off, just like with the binomial distribution, you have to determine whether or not the situation you're looking at is actually one where the geometric distribution would be appropriate. So there are 4 requirements that have to be satisfied in order for you to be able to use a geometric probability. Now the first requirement for the geometric setting is that each observation must fall into one of 2 categories, and we typically refer to these categories as success and failure. So this first requirement is exactly the same as the requirement that we have for our binomial setting. The second requirement is that the observations are independent. Again, this is also a requirement in the binomial settings. We haven't looked at anything different here yet. And the independence requirement simply means that whatever occurs in the first observation or the second observation and so on has absolutely no impact on any of the other observations. The third requirement is also one that we have for a binomial distribution, and that is that P, the probability of success, must be the same for each of our observations. And hopefully this is something that you've already thought about, but if P is the same for each observation, then that must mean that the probability of failure is also the same for each observation, since the only 2 outcomes are success or failure. Okay, the final requirement for the geometric setting, sorry about that, I got briefly interrupted. The final requirement for the geometric setting, and this is where the geometric setting differs from the binomial setting, is that we are interested in looking at the number of trials that were required to get the first success. So we'll do an example in a minute so you can see exactly what this means. One of the especially nice things about the geometric distribution is that the probability formula for it is really easy to remember. So anytime you're trying to calculate a geometric probability, again, that is the probability that the first success occurs on some trial, then the formula is going to be the probability that x equals n, where n is the number of the trial you're interested in, and the probability that the first success occurs on the nth trial is simply equal to 1 minus p, and 1 minus p is the probability of failure. If p is the probability of success, 1 minus p must be the probability of failure, and it's going to be 1 minus p to the n minus 1, because that means that if you're looking for the first trial where you have a success to be on trial n, then all of the trials before that must have been failures. So n minus 1 trials had to result in a failure. So you're going to do 1 minus p to the n minus 1 power, and then you multiply by p. So just to reiterate what this all means. This first part, 1 minus p to the n minus 1, that's just all of the failures that have occurred. And then on the nth trial, there's the first, there's the first success that occurs. So this is a pretty simple formula to remember. Alright, so I want to finish up with one quick example. So here's the question. We want to calculate what the probability is that the first 5 will occur on the third roll of a 6-sided die. So if we want the first 5 to occur on the third roll, that means that on roll number 1 and roll number 2 we got anything other than 5. So before we do this, we of course need to make sure that this really is a geometric setting. So first of all, we need to make sure that we have only one of 2 outcomes, success and failure, which we do in this case. Success means we roll a 5, failure means we roll something other than a 5. We also need to make sure that all of our trials are independent, which they will be, because what you roll on the first roll has no impact on the outcomes of any of the other rolls. We need to make sure that the probability of success is the same for each trial, which again it is, because if a success for us is rolling a 5, then that probability is always 1 out of 6 for each trial, and the probability of failure is then 5 out of 6. And finally, we need to make sure that our variable of interest is that the number of success, or the first success occurs on some nth trial, which is exactly what we're looking for. We want the first success here to occur on the third roll. So let's go ahead and calculate this. If we want the first success to occur on the third roll, then in this case the probability that we're looking for is the probability that x equals 3. So that means we've had 2 failures before we get our first success. So then we're going to use our formula, again, which that is 1 minus p in this case. Alright, p up here. P is 1 out of 6. So we've got 1 minus 1/6 to the n minus 1 power, and in this case is 3. So that's going to be 1 minus 6 squared times our probability of success on the third attempt, and that's just 1 out of 6. So that means then we've got 1 minus 1/6 is 5/6. So we've got 5/6 squared times 1/6, which is 25 over 36. And then I'm going to have to think about what 36 times 6 is. Just a second. Okay, so this ends up being 25 over 216. And that's all there is to it.